go. All right, so the theme in chapter 22 is nitrogen. And so much of this you already know. What I've drawn here is an alkyl amine with an alkyl group on it. This is a primary amine. Two alkyl groups make it a secondary amine. Of course, three alkyl groups make it a tertiary amine. But if you have four alkyl groups, then it's an ammonium ion. Of course, the thing that unifies the primary, secondary, and tertiary amines is they all have lone pairs on nitrogen, and amines are basic. And in general, alkylamines have positively charged conjugate acids whose pKa's tend to be in the range of 11. So the pKa of most ammonium ions is around 11. So what we want to start talking about is, how do you know how basic an amine is? Can you rationalize amine basicity using stuff that you already know? And one of the most useful tools for rationalizing amine basicity is to think about what makes a lone pair higher in energy or lower in energy. Things that spread out electron density, that delocalize electrons, are going to make a lone pair lower in energy and therefore less reactive and therefore less basic. An example of that would be to compare the basicity of ethylamine versus aniline, which is phenylamine or aminobenzene. In ethylamine, the lone pair is localized. You would predict that the alkylamine should be roughly sp3 hybridized, that the lone pair should be in an sp3 orbital, and it's not participating in any resonance. In contrast, for the aniline, you would predict that the lone pair would be in a p-type orbital where it can be resonance stabilized, and the reason it's in a p-type orbital is because it's adjacent to the pi bonds of the aromatic ring. And I can draw some arrows to show you how that resonance delocalization would happen. I'll just highlight the three other carbons that lone pair can be delocalized on. So the fact that the lone pair in aniline is resonance stabilized means it's lower in energy and therefore less reactive as a base, less basic. And we're going to see in general that being a good base is pretty similar to being a good nucleophile. The difference is bases attack hydrogens, attack protons, nucleophiles attack carbons. But in general, what makes something a better base will also make it a better nucleophile. So a nitrogen that's less basic should also be less nucleophilic. So yeah, you would predict that the aniline should be more basic. The alkylamine, ethylamine, should be more basic. Okay, does that make sense? So we can use other similar ideas to distinguish between structurally related molecules. So, for example, here's aniline again. You already know that the lone pair on aniline is resonance stabilized. I'm going to draw two different substituted anilines, one of which is got a nitro group here at the para carbon, and one of which has, let's go, an alkyl group at the para carbon. What do you think the effect of the nitro group should be on the basicity of the aniline, nitrogen? Should it make it more reactive or less reactive? Less, okay. Why? you know that the nitro is an electron withdrawing group. That means it can accept electron density from the benzene ring. That would tend to make the benzene ring, the electron withdrawing group makes the ring more electron poor, which makes it more able to accept electrons from the aniline nitrogen via resonance. And you can actually draw that process happening. Lone pairs kick down here, rearrange the pi bonds, and electrons move out onto the oxygen. I'll draw just one of those resonance structures here. And you can see that because of the nitro group, the lone pair has an additional place to be by resonance. Okay? So increased delocalization, increased ability of the benzene ring to accept lone pairs from the nitrogen. Yeah, you expect the nitroaniline to be less basic than aniline. What about the methyl group, which is an electron donating group? Where do you expect it to go? Ahead.
I would suspect it to push the electrons towards the aniline.
Okay, good. And what do you think that would do to the stability of the lone pair?
Will make it less stable.
Excellent, good, yeah. So this one is less, well, the conclusion is that the electron donating group makes the ring more electron rich, which means it is less able to accept electrons from the aniline nitrogen, and therefore the lone pair is less stable, which would make the alkyl substituted aniline more basic. Okay? So you can use the idea of electron donating groups versus withdrawing groups to stabilize or destabilize lone pairs as well, and then rationalize how reactive they should be. Go ahead.
Is that dependent on them being in the para position, or will that be influenced based on?
Is that dependent on them being in the para position? Good question, and you would predict for resonance electron withdrawing or donating groups, ortho and para should have a bigger effect than meta. It turns out the question you've asked is a subject that attracted a lot of interest in OChem over the past 60 or 70 years, and we talk about it some in our class 552, but we'll skip that here. Yep. Because there's a couple of things going on when you do that. You have to account for not only the resonance stuff, but if you move to meta or para or ortho, you're also increasing the ability of an electronegative, increasing how close an electronegative atom is. So you've got this sort of opposing inductive effect that can play a role sometimes too. So it gets a little complicated. For our purposes though, we wouldn't be making comparisons like that. Okay, good. Others? All right, you can use the concept of resonance delocalization as well to understand why amides are not very basic or very nucleophilic. So same alkylamine that we've been dealing with, and then this is an amide. The alkylamine is way more basic than the amide. The amide is not a base, generally not a base or a nucleophile, and the reason is the lone pair is delocalized with that adjacent carbonyl oxygen to give you this resonance structure where the negative charge is on the oxygen, where there's a negative charge on the oxygen and a positive charge on the nitrogen. So again, a resonance stabilized lone pair means the lone pair is lower in energy and therefore less reactive. This also illustrates an important point, you might be tempted to look at that nitrogen and say, oh, that nitrogen is surrounded by four things, three sigma bonds and a lone pair. Therefore, it should be sp3 hybridized. And you would be right, except for the fact that the adjacent pi bond with oxygen makes it so resonance can occur. Resonance is stabilizing, but for it to occur, the lone pair must be in a p orbital. So you need to get used to and actually good at recognizing when nitrogens are in p orbitals, and that's when they are adjacent to pi bonds, where the nitrogen itself is not already participating in a pi bond. Okay, you've seen this kind of thing a little bit before, amides versus regular amines. In fact, that was the basis of something I told you just a couple of days ago. You'll recall that I told you that when you try to do the Friedel-Crafts reaction on a benzene ring that has an amino group on it, the problem is you don't get the desired product because the aniline lone pair attacks the aluminum, generating this sort of weird Lewis acid-Lewis base complex in which the nitrogen's bound to the aluminum. However, if you first modify the aniline and convert it into the corresponding amide, resonance delocalization with the adjacent carbonyl group lowers the energy of those lone pairs to the point that the competing reaction with the aluminum doesn't occur, and the Friedel-Crafts reaction proceeds as normal. So you can get the expected ortho and para products respectively. And the reason that's working is because of resonance stabilization, literally lowering the basicity and nucleophilicity of that nitrogen. Okay, you can also, go ahead.
What reaction would you do to change an amine into an amide?
All right, yeah, if you wanted to make an amide, there's a couple of ways that we learned to do this. This is from chapter 16. One way would be to take the amine and react it with an acid chloride. In that reaction, the amine attacks the carbonyl carbon. You get a tetrahedral intermediate, a leaving group leaves. That would make the amide. That's nucleophilic acyl substitution. Another related reaction is the coupling of an amine and a carboxylic acid using the coupling reagent DCC, which we learned about in chapter 16, and that would give you the same amide product. So got a couple of options to make the amide, both of which work. You can use aromaticity to think about amine basicity, and this is a problem I think that was on your problem set. So this molecule, imidazole, has two nitrogens, and the problem was which nitrogen is most basic. And you can answer this problem in a couple of ways. You can consider the relative energies of the two lone pairs. Alternatively, asking which nitrogen is most basic is the same question as asking which conjugate acid is most stable. Understanding that the most stable conjugate acid will have come from the most reactive nitrogen. So I'm going to draw the two conjugate acids that you can get by protonating either nitrogen. We'll protonate the one on the left to get this conjugate acid, and then we'll draw the one where we'll draw the conjugate acid where we have protonated on the right. Okay, so let's go at this question from the perspective of the conjugate acid. Which conjugate acid do we think is most stable? What do you think? Go ahead.
One on the right,
One on the right. Good. Why do you say that?
because there is a double bond there, so it can, so the electrons can move a bit.
Okay. This is actually a resonance stabilized cation, which you can see just by moving the lone pair over here and then putting the pi bond on the other nitrogen. So that's one reason to expect this conjugate base to be more stable. It is indeed a resonance stabilized cation. That's not all that's going on here. What else do you notice? Go ahead.
The lone pair on the nitrogen with the hydrogen is in a p orbital because it's next to some pi bonds, but the nitrogen is already in a pi bond because its lone pair is in an sp2 orbital, so that makes it more likely to react with the hydrogen.
Okay, good. So you're thinking over here, saying this one's in a p orbital, this one's in an sp2 orbital. This one you're saying is stabilized by resonance. What else do you notice about it? What would you call this ring? Go ahead.
Aromatic ring.
Yeah, and you know that that's aromatic because it's cyclic, it's fully conjugated, and it's got 2, 4, 6 electrons, right? So aromaticity stabilizes lone pairs. If you come over here, one of the things you notice is that the conjugate acid where we protonate on the nitrogen on the right is still aromatic. The problem with protonating the nitrogen on the left is that this one is not aromatic anymore. The nitrogen that got protonated has to be sp3, so the ring is not fully conjugated. So, just based on comparing conjugate acids, you could conclude the conjugate acid on the right is more stable, therefore the nitrogen on the right is more basic. And that's true. The alternative explanation is to focus on the lone pairs, as we were already discussing. The lone pair that's in a p orbital adjacent to the pi bond is stabilized by resonance and aromaticity. The lone pair in the sp2 orbital is localized, therefore not stabilized by resonance, therefore higher in energy, therefore more basic. Okay. Let's see, one more example maybe of basicity. And this is going to draw on a principle you learned in 351, but it's maybe been a while since you thought about it. So here is a base called piperidine. We actually use it in our lab for some things maybe we'll talk about later this semester. And here is another base called pyridine. You can rationalize the difference in basicity. Well, let's actually just illustrate that difference in basicity. If I draw the conjugate acid of piperidine, it looks like this. It's an ammonium ion. If I draw the conjugate acid of pyridine, it looks like this. The pKa of that proton is 11.1 for piperidine, but 5.3 for pyridine, meaning the pyridinium ion is much more acidic, which means that it's that the corresponding conjugate base is less reactive, more stable, less basic, right? So let's see if we can rationalize that. Both of these lone pairs are localized. They are not stabilized by resonance. Now, it is true that in pyridine, the 3 pi bonds of the ring are part of an aromatic pi system, but that lone pair is not. It's in an sp2 type orbital, orthogonal to the pi system, not stabilized by resonance. In contrast, the lone pair in piperidine is in an sp3 orbital. Both are localized, the only difference is hybridization. And the reason and so the hybridization is what makes a difference there. Apparently, having more S character, the sp2 orbital has 33% S character, whereas the sp3 has 25% S character. I think I said that wrong. sp2 has 33%, sp3 has 25% S. S orbitals are lower in energy than p orbitals, so simply by averaging, an orbital that has more S character is lower in energy. So that means having 33% S character is enough to lower the energy of the lone pair in pyridine relative to the lone pair in piperidine, and that's why the corresponding conjugate acid is more acidic. You saw this, I think, when we compared the acidity of, in 351, I think you learned that the pKa for a CH proton isolated from other things is around 50 for an sp3 carbon, but around 40 for an sp2 carbon, and then around 25 for an sp carbon. So hybridization can make a difference, and you can use that as an explanation for basicity. Okay. With that in place, I now want to spend just a few minutes talking about some interesting amines. I do this not so that you can memorize structures, but because some of you aspire to prescribe medication someday. And I feel like if you do, you ought to have at least seen some structures and have some ideas about them before. Now, your average family practice doc is probably still not thinking about the structures of the molecules that he's prescribing, and that's fine. But it's good to have some foundation so that if you need to know more, you can learn more. So some of you still need to take the test, and when you do, you might find yourself nervous. Sometimes when humans are nervous, their heart starts racing, and you get something like a fight or flight response that's sometimes associated with your body secreting this molecule, which is called adrenaline. Now maybe you're like, no man, if I need adrenaline, I'll go snowboarding instead of taking an OChem exam. And I'd say that's fine, more power to you. But maybe, anyway, this is adrenaline. There's a core structure in adrenaline that I want you to see. You have a benzene ring, a phenyl group, and a nitrogen. And there are a lot of molecules that have similar properties that share that structure. For example, a related hormone to adrenaline is called noradrenaline. Other words for adrenaline are epinephrine. Epinephrine and norepinephrine, same thing as adrenaline and noradrenaline. Noradrenaline lacks the methyl group on the nitrogen, so noradrenaline is a primary amine rather than a secondary amine, but it still has that phenyl ethyl amine type structure. And you'll see some similarities when I draw the structure for another molecule that is in the news a lot and has devastating sort of long-term effects, and that's methamphetamine. It has the same phenyl ethyl amine structure. It lacks the OH group, and it has an additional stereocenter. But you could see, just based on structural similarities, that you might imagine them targeting the same sorts of receptors and pathways. I don't know really anything about adrenaline, noradrenaline, or methamphetamine biochemistry, but you can see by their structures that they're similar, and so you wouldn't be surprised to see sort of similar impacts. Another class of amines that we've talked about are neurotransmitters. There were a few of these we talked about when we discussed decarboxylation. I'll just show you, it reminds you of one of them. What I'm drawing for you now is the side chain, well, I'm drawing for you the amino acid tryptophan. The side chain with the 2 rings on tryptophan is called an indole ring. I'm worried I'm going to get that wrong. So this is the amino acid tryptophan. We showed you that with the help of an enzyme and the cofactor PLP, we can decarboxylate, that's remove the carboxylic acid group to generate just the amine. Oops, too many, there we go. And this is the neurotransmitter serotonin. And dopamine is made from a very similar pathway. Both of them are primary amines that I think, I'm sorry, I made a mistake. I'm missing a carbon. That's going to irritate all of you, but I don't care because I can't leave it like that. I will be embarrassed to send this out into the world on the internet if I get the structure of tryptophan wrong, right? In my lab, we do a lot of peptide and protein chemistry, so my students will laugh at me if I get the structure of tryptophan wrong, and then I will have to be sad. So there you go. There's serotonin, and notice that serotonin has an aromatic ring and an ethyl group and a nitrogen. So it's kind of got that same structure as well. And so you're seeing biology use sort of similar shapes and functional groups to deal with similar types of things in your brain. When we introduced serotonin, I talked briefly about selective serotonin reuptake inhibitors, which are used for depression and other things. These, interestingly, though they're not mimics of serotonin, they are not intended to do what serotonin does. They just prevent your neurons from taking serotonin back up inside them, leading to an overall increase in the level of serotonin in your brain. But interestingly, these molecules are also amines. So I'll just draw a couple of them for you. These aren't really to memorize, but just to see the structures. One of the more famous ones is called Prozac. This has a benzene ring. The adjacent carbon has a stereo center, and there's an amine with a methyl group on it. That's not really an ethylamine, that's 3 carbons, propyl. And then let's see, there's an oxygen, another benzene ring, and over here a trifluoromethyl group. I've drawn it here in its free base form. The term free base we use to describe the molecule when it has a lone pair on it. Normally, it would be sold and marketed as the HCl salt. So to show you what that would be, I just protonate on the nitrogen with HCl, and then the counter ion is Cl minus. Another common SSRI is Zoloft. This is, the trade name is sertraline, or the brand name is Zoloft, the trade name is sertraline. It's got a benzene ring with 2 chloros on it, a bond to a stereo center that's a 6-membered ring there, another benzene ring here, and then there's the amine there, also with a methyl group on it. And let's see, this is also sold as the HCl salt. And the reason people do that for drug molecules is often the amine form, the free base form, is less soluble in water than the hydrochloride salt. The hydrochloride salt is often crystalline. It's easier to formulate, package into pills, and transport. One other thing I forgot to tell you. Some amines are smelly. So short molecular weight amines like trimethylamine smells like fish. And so, and you've all smelled sort of the smell of seafood. When someone smells, oh, that smells fishy, you know what they're talking about. You're likely smelling an amine. So we usually go down to St. George for New Year's, and some of Amber's family comes with us, her brothers and their families, and they were like, "Hey guys, let's go down to Mesquite and go to one of the buffets at the casino." I was like, "Okay, well, my sons wanted to go, so I'm like, fine," because they're going to have prime rib and all the crab you can eat, and I'm not really. Maybe you think I'm nuts, but prime rib's kind of fatty. I don't really like it. And fish has just never really been my thing. So I went and just sort of sat there while they had great piles of crab legs in front of them. And there were, big, of course, containers of molten butter to dip the crab legs in. I guess anything would taste good when saturated with butter. But also there's lemons everywhere, okay? Why the lemons? What are people doing with lemon juice and fish? It's actually pretty common. Well, it tastes better that way. That's maybe part of it. Lemon is kind of a nice flavor, some tartness, some acidity. But lemon has citric acid in it, which is a carboxylic acid. What is that carboxylic acid going to do to the fish smell? Going to protonate the nitrogen, turn it into the ammonium salt. Here's the anion. HA is citric acid. The neutral amine is volatile and less soluble in water, so you can smell it. The positively charged ammonium salt is very soluble in water, and it's less volatile, so it's less stinky. So one of the reasons people have lemons around with fish is if you put lemon on your fish, it's not going to smell or taste as fishy. Why you would deliberately eat fish while not wanting it to be fishy is maybe beyond me. But again, the only fish I ever really had growing up, my mom made us fish sticks occasionally, but my mother does not like to eat anything that resembles in death what it once was in life. She's not a moral vegetarian, she's a grossed out vegetarian. She just doesn't like meat. So anyway, so I have limited experience with fish. But if you want to try this experiment, you could go buy some salmon from Costco, or you could go get a carp out of Utah Lake, wrap it up in foil and stick it in your trunk of your car for a month, and then smell it, and then put lemon juice on it and smell it again, and see, it's probably better with the lemon juice. As to whether you can put lemon juice on the fish before it rots, and then if it doesn't smell bad, I don't know about that one. Somebody ought to do that experiment. Yes, somebody did ask for extra credit this morning for doing that experiment. I said no, but still interesting to do. Go ahead.
I've heard milk can also get rid of the fishy taste. Do you know how that
Milk can get rid of the fishy taste. I'm not sure about that. Milk has a lot of proteins, casein and some other proteins in it that are just good at non-specifically absorbing things, so that's maybe what's going on there. Yeah. Okay, well, now we need to get back to some chemistry. We're going to introduce a new reaction and then one that you've seen before. So let's talk about amine synthesis. And we got a major problem, and that is that you think that amine synthesis should be easy. Why don't we just start with ammonia and do the SN2 reaction where nitrogen attacks the bromine, attacks the carbon that has the bromine, bromine leaves. You get an intermediate that looks like this, that's positively charged, and then Br minus removes one of the protons, and then you end up with this alkylamine. And that reaction is reasonable, but it has a problem. And that is that alkyl groups are electron donating groups. Therefore, the lone pair on an alkyl amine is more basic and nucleophilic than the starting material. Whenever you're in a situation where the product is more nucleophilic than the starting material, you've got to watch out because the product will start to compete with the starting material for your remaining reagent, and you will start to see over-alkylation. Meaning you get some of the secondary amine, you get some of the tertiary amine, and you even make some of the quaternary amine in sort of an uncontrolled fashion. Over-alkylation is the problem with direct alkylation of amines. You might say, could I just use one equivalent and would that work? And the answer is it doesn't really well. So organic chemists need a workaround because there are a lot of uses for primary amines in subsequent synthetic reactions. We need a reliable way to make primary amines without having to over-alkylate. So enter a new reaction called the Gabriel synthesis of primary amines. And this is kind of an elegant synthesis because it takes advantage of resonance stabilization to prevent over-alkylation. So rather than use ammonia, in the Gabriel synthesis, you start with this nitrogen, this molecule, which is called phthalimide. The pH is sort of silent. I'm not sure if you're supposed to pronounce the F and the TH sounds at once. Good luck with that. You're going to spit all over the place. So, and I don't know what language it comes from, but there you go, phthalimide. First of all, notice that the nitrogen there, the lone pair on the nitrogen is resonance stabilized, meaning it's not particularly nucleophilic. However, interestingly, that proton on phthalimide has a really low pKa of around 10. It's much more acidic than you would expect for an amine, and that is because the corresponding conjugate base, so you could use just OH minus to remove that proton, the corresponding conjugate base is resonance stabilized. So that nitrogen now has a negative formal charge and two lone pairs on it. One of the lone pairs is delocalized via resonance. And I'll draw not all of the resonance structures, I'll just draw one of them, but you can see one of them has the negative charge out on the oxygens. Out on one of the oxygens, you can draw another resonance structure where the negative charge is on the other oxygen too. Okay, so this is a negatively charged conjugate base. It's nucleophilic, but it's not nucleophilic on the resonance stabilized lone pair. It is nucleophilic on the one that's perpendicular to the pi system. So what you can do then, having generated that nucleophile, is do the SN2 reaction with the lone pair that's not resonance stabilized, breaking the pi bond, the carbon bromide sigma bond, making a new nitrogen carbon bond. Once you've done that, though, the lone pair that remains on the nitrogen is still resonance stabilized, and it's still, stabilized, and it's not nucleophilic because of that. So once we get here, there is no danger of over-alkylation. So we can stop. Now that's not our desired molecule. We would really like to get to the primary amine, and if we didn't have a solution, this would be a dumb reaction. Fortunately, we do. We can use water and hydroxide now to do a reaction that you learned in chapter 16 of the text, amide hydrolysis, and that will release the primary amine, and the other side of the molecule will be this dicarboxylic acid benzene ring. I could show you the mechanism for this reaction. I don't really think it's worth our time today. The OH minus attacks the carbonyl carbon. You get a tetrahedral intermediate, which kicks off this nitrogen. The negatively charged nitrogen is going to be resonance stabilized, which is why it can leave. So that'll get you started if you wanted to work through that on your own. I don't think it's particularly useful to worry about today. But this is how you get a primary amine, and there was absolutely no danger of over-alkylation. So this is a common way that organic chemists prepare primary amines. The second reaction that I just wanted to mention is one that you learned in chapter 14. So this is a review. This you can use to make primary and secondary amines, and again, there is no risk of over-alkylation. In reductive amination, you use an amine and then some organic acid, like acetic acid, to convert the aldehyde and the amine into the corresponding imine. And in the imine, we've made two new bonds. We've made carbon-nitrogen sigma and pi bonds. And there was no risk of doing that more than once to the nitrogen. In the second step, you do a reduction reaction. The reagent we've used was sodium borohydride. Your text may introduce another reagent called sodium cyanoborohydride. This is just a less reactive version of sodium borohydride. This delivers a hydride to the carbonyl carbon, and then the nitrogen picks up a proton. That's going to reduce the pi bond and leave us only with a new the new carbon-nitrogen sigma bond. So we make the carbon-nitrogen sigma bond here, we reduce the pi bond here, we're left with this carbon-nitrogen sigma bond, and you see we've taken a primary amine and we've converted it into a secondary amine, and again, there was no risk of over-alkylation. So organic chemists literally use this strategy all the time in the lab when we need to make amines in a controlled way. And you should be aware of and know how to use both of these. Okay, with that, I now want to tell you a story about the birth of the modern chemical industry. And I didn't paste the stuff into this set of slides, so I'm going to go to my previous set of slides, but I'll post the notes accurately a little bit later. Okay, so in the 1850s, a young man named William Perkin was in his lab at home. He was 19. I don't know how many of you had a chemistry lab in your house at 19. Who knows what his parents were doing. But he was trying to make an anti-malarial molecule called quinine. Malaria then was a terrible disease that killed millions of people. I mean, it's still a major problem today, but developing an anti-malarial drug was an important goal. His starting material, he intended to start with aniline, which is this aromatic ring, and a nitrogen. And he was trying to use potassium dichromate to do the reaction. Now, potassium dichromate, you've seen before in 351, it oxidizes a primary alcohol to a carboxylic acid. It's like CrO3. Really, there was actually no chance of this working. I'm not showing you the structure of quinine, but it's quite different from the structure of his starting material, and there was no way that potassium dichromate was going to do it. He didn't know that. A lot less was known about chemistry at the time. It seemed like a reasonable thing to try, and he had time, so why not? What he didn't know is that his sample of aniline was actually contaminated with two related molecules that had similar boiling points. These are the toluene versions of aniline, where a methyl group is ortho and or para to the ring. Back then, you couldn't just order a molecule and expect it to show up in 100% purity. You had to actually separate molecules from each other, often by distillation, where small differences in boiling point were very difficult to overcome, and that's why his sample was contaminated. In any case, the reaction failed, and he ended up with a flask of a black solid, which usually means, sorry pal, try again. And If you have a lot of resources, you throw the flask away. If you don't, you start trying to scrape out the stuff out of the bottom and dissolve it. Fortunately, he didn't throw it away. He tried to dissolve the stuff that was at the bottom of the flask with alcohol or ethanol. And as he started rinsing it out, the alcohol turned purple. And he was like, ooh, purple. Now, you and I see purple and we're like, that's pretty, no big deal. This was the 1850s, and at the time, there weren't that many readily available purple dyes. In fact, purple was a pretty rare color. The way you got it was by diving into the ocean and getting sea snails or mollusks and crushing them and extracting indigo or Tyrian purple. In fact, if you read in the New Testament in the book of Acts, one of Paul's earliest supporters was a woman named Lydia, who was called a seller of purple. You can tell she was a successful small businesswoman because she sold a very expensive dye. Purple was associated with royalty because nobody else could afford the color. So that's why he was like, ooh. And as most teenagers do, he decided to start a factory, which he did in 1857, repeating the reaction, making this molecule. He retired at the age of 36 as a very wealthy man. His name is still honored in the Royal Society of Chemistry in Britain. There are awards given out in his name. There were journals named after him, all from this failed reaction that made a pretty color that people would pay a lot of money for. But that discovery led to a surge in chemical research and an attempt to make molecules that could be useful as dyes and drugs and other purposes. So I'll just show you the structure of the molecule that he made. He didn't know this. Its structural solution came much later with modern analytical tools. Here is a portion that came from the orthomethyl version. Here's the one that came from the paramethyl version. Here are the two portions that came from aniline. He wouldn't have predicted that this reaction happened. Its mechanism is sort of known, but isn't important to us right now. You can tell that this molecule should be colorful because it is highly conjugated. Highly conjugated molecules have gaps between HOMO and LUMO that are low enough, small enough, that a photon of visible light can excite an electron from HOMO to LUMO, and the photon gets absorbed. When photons of visible light get absorbed and others get reflected, that's when we see color. So this one reflects purple light, absorbs light elsewhere, and that's why it's purple. And everybody suddenly wanted to make a dye molecule. And so people got started, and a very popular class of dye molecules are the ones we're going to talk about next time, which are called azo compounds. They are very conjugated, but they have this characteristic double nitrogen with a double bond in between the two, with two aromatic rings on either side. And you can see how this would lend itself to experimentation, because if you could figure out a way to make this from two separate parts, you could mix and match rings on the left hand and on the right hand, and maybe you could make dyes that have different colors. So this one is red. And people got very creative. You can see the question they were asking here. What if we stitch two of these azo compounds together in the same molecule? Do we get a different color? And a lot of this work happened in Germany. And it was about this time that a chemist named Paul Ehrlich was using dyes as a method for staining cells. If you've ever looked under a visible microscope at a slide of cells that are not stained, you can't see very much because cells are mostly transparent and you can't really see any of the subcellular organelles. But if you layer a dye on top of the cells, you can get some contrast. And Paul Ehrlich was doing that when he discovered that a certain cell type would take up a certain dye selectively. I'll tell you just a bit more about that story next time, and then we'll dive into how to make azo compounds. With that, good luck on the exam. I will see you Friday.